Let me show you the next example. Let's execute this query that selects from orders. Inner join temporary table department. Order.department ID equal to department.department ID with max TOP set to 1, so the query can use only one CPU core. Like before, I reset wait stats and finally collect the amount of CX packet weights. Let me show you what is in the temporary table department. This table has 4 rows. Department IDs from 0 until 3. Let's create this table. Let's execute this query with max TOP set to 1. The CX packet wait time is 0. Since the query executes serially, there is no parent task or child task that could wait on CX packet wait. Let's look at the messages. The query took 336 milliseconds to complete. CPU time is 344 milliseconds. Let's execute again. CX packet wait time is 0. The query took similar amount of CPU time and elapsed time. Let's change the max degree of parallelism to 0 so the query can use all 4 CPU cores. Let's execute the query. CX packet wait time is 97 milliseconds. Query took 95 milliseconds. The CPU time is slightly higher than serial execution. The elapsed time, the duration, and the CX packet wait time is nearly the same. Let's execute the query again. CX packet wait time is 95 milliseconds and elapsed time is 95 milliseconds. This shows it is just the parent task, the coordinator, waiting with CX packet wait type while other threads are processing. Let's include the actual execution plan. Let's execute the query. Let's analyze the execution plan. Right click, properties on clustered index seek. There you see each thread processed 100,000 rows while thread 0, which is the coordinator, did not process any rows. Let's change the query slightly. Let's comment out 2 rows from this temporary table. So we process department IDs 1 and 3. Let's create this table. Let's execute the query serially first. Let's remove the execution plan. Let's execute the query. CX packet wait time is 0. The query took 169 milliseconds, nearly half of the time when we executed with 4 rows. Let's execute again. There you see 166 milliseconds and CPU time is 172 and CX packet weights are 0 because the query is executing serially. No parent task to wait on CX packet weights. Now let's execute the query in parallel. When I execute the query, it will use all 4 CPU cores. The wait time, the CX packet wait time in this case is high. It's no more 92, but the query still completes in 90 milliseconds. Let's execute again. The query still completes in 91 milliseconds. The CPU time is similar to what we saw before with serial execution, but the CX packet weights went up. Let's include actual execution plan. Let's execute this query. Let's analyze the execution plan. Right click properties on clustered index seek. There you see only 2 threads processed 100,000 rows while 3 threads were waiting. This is the reason why CX packet wait time is 3 times higher than the duration of the query. Even though the CX packet wait was high during parallel execution, parallel query took nearly 2 times less duration than serial query, but both took nearly same amount of CPU. So high CX packet weights in this case is not a bad thing. Let me explain this in a different way. Let's say we are working for a large employer and our firm is organizing a company meeting, and our Mario, the nice colleague from the administrative services, is responsible to make sure lunch, the midday meal, is efficiently consumed by all the 4,000 participants. I mean, in least time, so the company meeting can continue quickly after the meal. These 4,000 participants are from 4 departments, 1,000 participants from each department. Mario arranges 4 food service counters where employees can order their custom-made sandwiches. During mealtime, Mario routes each department to a specific counter based on their department ID. 4 counter processes 100,000 participants each, and they are all served more or less at the same time. The company meeting continues efficiently after the lunch. Mario gets a bonus. Let's say on a different day, Mario is asked to organize food again, and he makes the same 4 food service counter plan since we already own those 4 food service counters. Think of food service counters as CPU cores. That day, instead of participants from 4 departments, there were only participants from 2 departments, 2,000 participants. What if Mario routed them to 2 food service counters based on their department IDs? We know this will not be efficient since 2 other counters will be idle, underutilized. Think of counter idle time as CX packet wait time. If Mario's manager is knowledgeable, then he or she will question why Mario did not route those participants from 2 departments to all 4 food service counters. If Mario's manager is not knowledgeable, then he or she might agree 2 counters were underutilized, increasing the CX packet wait time, and further agree to Mario's suggestion about using only 1 food service counter by setting max degree of parallelism to 1, so there is no counter underutilization, queuing all 2,000 participants to the same counter, in effect doubling the meal consumption time. Of course, the management will not be happy and will cut Mario's bonus if he did that. Let's help Mario to distribute the 2,000 participants to all 4 food service counters. Let's help SQL Server distribute 200,000 rows to all 4 CPU cores. Let's alter the query. Instead of a join with department table, let's introduce a subselect. Select department ID from department, and we say where department ID in. Let's set statistics time on. Let's execute the query to populate the temporary table. This time we populate all rows, and let's execute the query. The CX packet time is very high. The elapsed time is not 92 milliseconds like we had with join. Let's inspect the execution plan. Let's execute the query. Let's move the cursor to clustered index seek. Right click, properties. There you see all threads did not process even amount of rows. 1 thread processed 200,000 rows. So in fact, increasing the CX packet wait time. While this thread processed 200,000 rows, thread 0 and thread 3 waited with CX packets, and thread 1 and thread 4 waited half of its time with CX packet, increasing the CX packet wait time significantly. Let's now change our query. Let's include primary key. Let's tell the optimizer that these values are unique. Let's create the temporary table. Let's execute the query again. Now you see the execution time has dropped and the CX packet wait time also dropped. Let's inspect the execution plan. Right click properties. There you see SQL Server processed 100,000 rows over all the 4 threads. Let's now comment out 2 rows from this temporary table like we did before. Let's create the temporary table and let's execute this query. The CX packet wait time is high like before, and in the messages you see the execution time is not lower. Let's go to execution plan, right click properties. There you see again 2 threads processed all the 100,000 rows each, and 3 threads waited. The coordinator waited and 2 other threads waited. In this case, 2 threads are idle along with the coordinator, increasing the CX packet wait time. In this case, neither the join nor the subquery helps SQL Server process those 200,000 rows across 4 threads. It is processing always using 2 threads, increasing our elapsed time. Our goal is to spread this 200,000 rows across 4 threads. Let's rewrite the query further. Let's simply include an in clause instead of a subselect or a join. Let's look for department IDs 1 and 3 like we did before. Department ID 1 and 3. Let's execute set statistics time on first, and let's execute our query. This query took 68 milliseconds, faster than our parallel query execution with a join or a subquery. Both cases took minimum 92 milliseconds to complete, and the CPU time is slightly higher. Let's inspect the execution plan. Right click properties on the clustered index seek. There you see the 200,000 rows are distributed across 4 threads, helping this query scale better. In this case, we also reduce the CX packet wait time. If you see, our CX packet wait time is very similar to the elapsed time, which means it is just the coordinator in our example weighted with CX packet wait type. By rewriting the query without reducing or disabling parallelism, again without running away from high CX packet wait time, we made the query perform well. We actually decreased the CX packet wait time without reducing max degree of parallelism and made the query perform well. How do you know if rice is fully cooked or needs more cooking? Usually we sample a single grain of rice, and if that is cooked, we take few more random samples, and if all of our samples are cooked, then we say the rice is cooked and ready to be served. On the other hand, if we taste and the first sample of rice is uncooked, then we don't take any more samples. We know it is not ready for prime time and we send it back for more cooking. Without reducing max degree of parallelism, by simply tuning the query for better performance, I proved to Mr. JLR that CX packet, direct result of inefficient parallel processing theory, is wrong. Mr. JLR asked me, when should one execute a query in parallel? Well, this is a good question. I think in most cases, you can make a decision yourself. In some critical cases, you should let your manager decide. I will show you an example. Let's execute our query with max degree of parallelism 1 and max degree of parallelism 0. So the first query will use single CPU core and the second query will use all 4 CPU cores. Let's set statistics time on. Let's execute the query. There you see the first query executing serially took 319 milliseconds, took 312 milliseconds of CPU. On the other hand, our parallel query took 137 milliseconds to complete. The query is quite fast, but it took extra CPU. Instead of 312, it took 375 milliseconds of CPU. This query doesn't scale very well like our query with like predicate, for which the execution time decreased by 1/4 when we used 4 CPU cores. But the duration of this query is a bit lower, which matters especially when such queries are called thousands of times inside a report or a billing job. If the query is running part of a report alone in the night, it might be okay to run the query in parallel. The only disadvantage is it takes a lot more CPU warming up the planet, if you believe in that. During the day, when the system has heavy activity, it might not make sense to run the query in parallel, since it will increase the overall CPU utilization without significant benefit. It all depends. When you are not sure about making a decision, ask your manager, giving him or her the information we discovered. First of all, your manager will be shockingly surprised. He or she will wonder, how come a SQL Server colleague gives me choice and simply doesn't disable max degree of parallelism? I told Mr. JLR that I will help SQL Server colleagues, developers and DBAs through my workshops and webcasts with all the information they need to make decisions, and will help them so they can provide that information to decision makers so the management can make informed decisions. And if they keep doing this, I am sure they will overtake Oracle colleagues' salaries and bonuses. One day, our colleagues will develop deep SQL Server knowledge and be able to see eye to eye an Oracle colleague and tell them that we are on our way to replace Oracle out of the data center. There are cases where you don't need to consult anyone and simply turn off parallelism for certain queries. Let's see an example. Let's execute this query with max degree of parallelism 1 and max degree of parallelism 0. So this query is limited to 1 CPU core. This query can use all 4 CPU cores. Let's set statistics time on and let's execute both of these queries. There you see the first query took 1.2 seconds elapsed time and the CPU is also 1.2 executing serially. The parallel query took 5 seconds of CPU time and 1.4 seconds elapsed time. This query takes more CPU and longer duration when executed in parallel. These queries should never be executed in parallel. Parallel query execution is a huge topic. There are more complicated cases than what I showed you so far. Let's search books online with keyword CX packet. Let's click on sysdm OS wait stats. There you see CX packet occurs when trying to synchronize the query processor exchange iterator. You may consider lowering the degree of parallelism if contention of these wait types becomes a problem. Question is, what is a CX packet contention problem? We might cover this contention problem, which involves complicated examples and more parallel query execution issues in future webcasts. Actually, all of it depends on your feedback. So if you are interested, do take time to send us an email expressing your interest in these topics. If we do not receive enough feedbacks, we might not show those complicated examples in webcasts. Like in the previous webcast, please send me an email if you want the example scripts. Be specific which example script you want. If you liked this webcast, tell your friends. Inform your local user community. Mention it in your blog. If we know more people are interested in our webcast, we will deliver more webcasts. Feel free to sponsor 5 euros safely with the PayPal donate button that you will find in the download page to help us cover our network bandwidth expense. If you notice other instructors and speakers simply copy these ideas and concepts without giving credit to SQLWorkshops.com by mentioning SQLWorkshops.com website link in their material and speeches, tell them people at SQLWorkshops.com will not be motivated to deliver future webcasts if they are not credited for their ideas and concepts, and this will be a loss for the entire community. We at SQLWorkshops.com appreciate your help. Ladies and gentlemen, on behalf of SQLWorkshops.com, I would like to thank you for viewing this webcast, webcast number 2. Please keep your feedbacks coming. Once again, time to say goodbye.